Very excited to have him with us today to guide us through the fundamentals of QML and demonstrate how we can start building intuition and even some practical models. Please join me in giving a warm virtual welcome to Jai Shah.
Uh, thanks, and thanks a lot for having me here today. Uh, I really look forward to a great UML session with all you guys. So, shall we get started with the session? It's already 1:40.
Sure. You can start.
Sure. So I'll share the screen, right?
Yeah.
I'm sharing the screen in full screen. Just let me know when it's visible.
Yeah, it's visible.
Okay, great. So again, thanks a lot for having me here today. Uh, and I already had a few, sessions with this Qiskit Fall Fest and this another one. And, I really love talking about quantum machine learning. And before we get into the details, I'll just talk about very briefly about, what I'm doing in quantum machine learning. All right. So I hold two positions. One is as a quantum machine learning researcher at BQP, which is a startup with headquarters in New York, and we also have a office here in Bangalore, and we have people from almost all over the world, working remotely with us and stuff. Uh, what BQP is doing is, we're using quantum computing and quantum machine learning for engineering simulations, right? So for as per target industries, you can think of aerospace and defense, as very prominent industries where these solutions are really useful, right? And I lead all everything quantum machine learning at BQP. Other than that, I'm the founder and lead developer of QRL, and QRL is totally focused on quantum reinforcement learning, right? And as you might have guessed, it's my favorite branch of all of AI, reinforcement learning. And it's already launched QRL QAI, which is a pip Python package, which you can just simply install with pip install QRL QAI. What you see beneath is one of the environments that the package offers. So right now it offers five gym style RL environments that you can actually explore. And what is QRL QAI? It is nothing but the quantum analog of OpenAI's Gym Python framework. So before OpenAI launched ChatGPT, they had launched something called Gym, which was completely focused on reinforcement learning, and QRL QAI is a sort of quantum analog of that. And the GitHub repo is there. Everything is open source. So I do insist that you should definitely check it out. Okay, that was my introduction, and today I'll just go through all the agenda of what's the stuff we are going to see today, right? So first of all, we will go through a very basic overview of all of quantum machine learning, right? I'll try to give you a bird's eye overview of what are the major branches, and what's going on in each of the major branch, and what are we trying to do there, right? And the little mathematics that I would need in the later section. So we will just lay the foundation of everything we need, for the rest of the session in the section one of overview of quantum machine learning. In the second section, we will go into the details of quantum neural networks, right? Because as you would see in the section one, if you understand quantum neural networks, you actually understand a very big chunk of quantum AI, right? So quantum neural, and that is the reason I've chosen quantum neural networks as a major topic for the session today, because I mean, if you get the essence of this thing, you understand a very big chunk of quantum machine learning. And inside this section two, we have five subsections, right? So first, I will help you understand the concept of quantum neural network by comparing it to a classical neural network. Then we will, see what are the building blocks of a quantum neural network in section 2.2. Then we will go for forward propagation, which will be a hand calculation, right? So from giving an input, to getting an output from a quantum neural network, what is the actual mathematics that is involved? We will solve the entire thing by hand. Then I will briefly touch on backpropagation, right? So what are the types of backpropagation and all those things, right? Uh, and in the final section, subsection of the second section, I will briefly also talk about what are the general challenges that you would face. If you go out there and try to train a quantum neural network by yourself, what are some of the challenges that you will most likely face, right? So we will end the second section with that, and I think there will be a half an hour break after that. Then we will have the hands-on session, which will be focused on quantum GAN, which is quantum generative adversarial network. And first, again, I will briefly talk about the theory of the quantum GAN, so that just to make sure that all of us are on the same page. And then once that's done, we'll go for the hands-on session, and we'll solve quantum GAN, and also there will be a final sort of assignment that would connect the theory that of quantum neural networks that will go through and the final hands-on session. So when you're getting out of this session, you will have something to look out for, something to solve for, right? Because I always believed in active learning, right? And that's the reason I'm trying to include a hands-on session, a simple assignment, and a calculation by hand. So you are just not seeing it things conceptually, or you will actually see the math that goes into quantum neural network. All right, so that paints the picture, right? Let's go to the first section, which is overview of quantum machine learning. Okay, so let me just, okay, laser should work. Okay, so the first part. So quantum AI, I've written a quantum AI. So obviously I've tried to, bifurcate quantum AI into three major branches. You can have more sub branches, and even in each of these branches you can have more branches, but just on a higher note, the entire field of quantum AI can be broken down first into quantum machine learning, right? So people who know classical machine learning know that even in classical AI you have classical machine learning and classical deep learning. And the reason we call it, different is because of the type of algorithms that are involved. And the same goes here as well, right? So, for example, in classical machine learning, you have algorithms like support vector machines and k-means clustering, right? Some of the example. Similarly, in quantum machine learning, you have the quantum counterpart of those algorithms like quantum support vector machines and q-means clustering. Uh, and again, if you notice, in this branch of quantum AI, a general thought process is just to use quantum computing or the mathematics of quantum computing to make the classical algorithm more efficient, right? So whether it's SVM or K means, Q means, right? A general essence is that a certain part of the calculation that is involved uh, in the classical algorithm, in the classical counterpart, what you do is you try to substitute some quantum calculation that will sort of speed up the process and make things more efficient, right? That is a general process, a general thought process in the framework of quantum machine learning, right? And also, if you have observed here, if you see these blocks that I have kept here, they are all in white background, but the one at the bottom here, Q boost and quantum Boltzmann, it's highlighted in yellow. And the reason is that all the other ones that you are seeing here, they are based on the gate model quantum computing, right? So all of these other methods are gate model quantum computing based quantum machine learning. But the yellow one that you see here is actually annealing based quantum machine learning, right? So quantum computing has different models of quantum computing, right? And the two most popular are gate model and annealing based quantum computing. And there are more to it. It's not limited to that. For example, continuous variable quantum computing, where the fundamental unit is not qubit but q mode, right? So we have a lot of variety in quantum computing. Uh, and so QBoost and quantum Boltzmann machine are the quantum machine learning algorithms that comes out of annealing based quantum computing, right? And again, if you know and if you have heard of XGBoost in classical machine learning, I mean, if you know classical machine learning, I'm 100% sure you have heard about XGBoost algorithm. The QBoost is sort of quantum version of that. And again, we have Boltzmann machines and classical machine learning. So again, these are the quantum variants of those algorithms, right? But again, just to recap, quantum machine learning, a general thought process that you will generally see is that you use some quantum computing mathematics, you introduce some sort of quantum part into the existing algorithm, so that you can speed up the computation, right? That is the general thought process. Okay, now let's come on to the second branch, which is let me use and it would be better. Okay, let's come on to the second branch, which is quantum deep learning. As you know that even in classical AI, deep learning is sort of more powerful than machine learning, right? Sort of something similar you can say here. Uh, Now in deep learning, it's a long branch. You have so many algorithms. You have so many important subfields, right? Like generative AI, computer vision, natural language processing, and no matter which classical algorithm you say, you will always see a quantum counterpart for it, right? So for example, you have classical neural networks, you have quantum neural networks here. If you talk about classical GANs, then you have quantum GANs here. If you talk about auto encoders, you have quantum auto encoders, and just leave all of that. We also have quantum GPTs, right? So we have even quantum versions of transformers and GPTs coming in, right? So no matter what classical algorithm you name, you will always see a quantum deep learning counterpart for it. And obviously, if you see here, you know, we have quantum neural network here that we'll be covering in depth today. Then we have quantum GANs that we will also see in the hands-on session. And there is a reason, that I have chosen quantum GAN here. I've listed it here, and I've chosen quantum GAN for the hands-on session. And one of the reason is that I wanted to highlight how quantum deep learning could be substantially different, from classical deep learning. So that was the reason. We will get back to that again, when we get to the hands-on session, and I'll talk about this. And quantum autoencoders is just another example, right? Okay, so that is quantum deep learning, and don't worry about quantum deep learning. We'll see and that what is quantum deep learning and how things are working, what people are trying to do. We'll talk about that in much more detail. And the final branch is quantum reinforcement learning. As I told you, it's my favorite branch. I love reinforcement learning. Here there are two things, right? If you know reinforcement learning, the framework of reinforcement learning revolves around an agent that does some action, and the action is executed by environment, and some reward is given to the agent, a good or bad reward based on the action. And over time, with this interactive environment, the agent eventually learns and solves the environment. If you don't understand any of this, it's all right. But basically, what we have in quantum reinforcement learning is you can have a quantum environment, right, and a quantum agent, right? So whatever are those components of the reinforcement learning framework, you can have a quantum part of it, right? So you can make your agent quantum, you can make your environment quantum, right? So that's how you can introduce quantum. That's one way of introducing quantum and quantum reinforcement learning. The second one is, as you might have guessed, having the quantum version of the classical algorithm. For example, q value here, right? So you have q table and value based algorithms and quantum reinforcement learning. Similarly, you will have their quantum counterparts in the quantum reinforcement learning. Again, same Q policy, right? So you have policy-based algorithms as well in classical reinforcement learning. You have the quantum version of it, right? And that's pretty much an overview of the field. So again, just to recap, in quantum machine learning, we are trying to introduce mathematics of quantum computing, some concept from quantum computing, and replace some of the parts or calculations of the existing algorithm to sort of speed up the computation or make things more efficient. That is a general thought process. Quantum deep learning is mostly revolves around quantum neural networks. We reach quantum circuits, and we will see all of it in much depth today. Quantum reinforcement learning, it's a more of research area yet, and you generally have two ways of doing things. Either introduce quantum as a major component framework, right, or like an agent or a environment, or you just use the quantum algorithm, right, of a quantum counterpart of the existing classical algorithm. So that was a very brief overview of quantum AI. There are many other things in quantum AI, but we will just try to keep things simple here, right? Okay. Now I'm sure you had previous sessions in this series of this Qiskit Fall Fest. So I'm really sure the previous speakers have already discussed this simple mathematics. But since we will be going through the hands-on calculation today, so I just wanted to provide a very quick overview of mathematics so that all of us are on the same page. Whoever is attending this session, all of us are on the same page. When we go into that hands-on calculation segment, right? So there are two things, when you come to mathematics of gate model quantum computing. Uh, One is states, right? The state of a qubit or a state of a multi-qubit system that you represent by this sketch or bras, or we can say bracket notation, right? And then you have quantum gates, which actually represents the operations that you perform on a quantum state, right? And this is basically linear algebra, simple matrix multiplication. Okay, let's very quickly touch all of it. So the first box that you're seeing here, that's cat 0, cat 1, scary and fancy looking uh, notations for something as good as a simple column vector, right? It's really simple. Similarly, you have here bra notations. Again, a scary fancy notation for something as simple as row vector, right? uh, but definitely, when you get into the calculations, you will really appreciate that you have these notations, because the normal notations would get really messy and difficult to handle. Again, with that said, bracket or the inner product. So the vector inner product that you have, this is how you represent it in a direct notation system, right? And obviously, it's a inner product. You have scalar output at the end, right? And if you see, if you really want to see how you get these answers 1 and 0, just take this vector, first one, car 0, take this vector, cat 0, right? And try to multiply it, you will get 1, yeah, right? Then you have auto product, right? Again, this is simple, you can substitute the vectors, you will get the matrix, nothing complicated. Now, this blue box that you are seeing, right? Uh, all of these operations that I just talked about are all single qubit operations, right? It's all single qubit system, right? But how you would you scale it to multi-qubit or two qubit or three qubit or multi-qubit system? And that's where we have tensor product coming in, right? So again, you can substitute these vectors with the the column vectors here in the notation. The important part is this tensor product notation, right? And what you'd actually do here is, you take the first element of the first vector, multiply it with each of the elements in the second vector. Then you take the second element of the first vector and multiply it with each of the elements in the second vector, right? And that's the reason, if you see initially the size of this column vector of cat 0 is just 2, but when you obviously move on to the higher system, it gets 4, right? So tensor product is a very important and crucial step here. And when you will go, into the head calculations, you will understand more of, I mean, this is very simple calculation, but when we'll go into the forward propagation part, this will be more helpful. Okay, so that was all quantum state, right? Now, let's move on to quantum gates. And up until all these sessions, I'm sure you've seen this guy, right? Hadamard gate that represents, mathematical metrics for quantum superposition, right? Which is a great example of a single qubit gate. Then you have C naught gate, right? Which is again an example of a multi-qubit gate, and you will have the C naught gate in the hand calculation as well, right? So we'll have that. Then again, if you see, I have highlighted RX gate here, uh, which is then example of a parameterized gate, and it is of super importance for us, right? Because I mean, we will see why, because we'll be talking in much depth here for this gate. And the way, because the reason it gets parameterized is because, it takes in this parameter theta, and, based on that, the value of the matrix is calculated, right? That's why it's parameterized. And this here, it just represents matrix multiplication, or, how you write matrix multiplication in direct notation, right? So this was a very brief overview just to, lay the groundwork for what we are about to do, in the next section. With that said, let's get to the quantum neural networks part, right? Okay. So I'm just assuming that, everyone here has a simple basic idea of what a classical neural network looks like, right? And we'll, again, what I'll do here is that I want to give you a side-by-side comparison of classical neural network versus a quantum neural network. So on the left here, you are having a classical neural network. On the right, what you're seeing can be termed as a quantum neural network, right? Let's do it. So the orange box that you are seeing here, right, that represents the input layer in each of the networks, right? So on the left, it's the input layer for a classical neural network. On the right, what you're seeing is the input layer for the quantum neural network. Again, we will go into the details of it. So, we'll don't worry about it. The second major component is hidden layers. So the yellow box that you are seeing here, on the left-hand side, it shows the hidden layers, the way it looks for a classical neural network. Similarly, hidden layers look something like this for a quantum neural network, right? And the final section, which is the output layer, right? So the green box again shows you the output layer for each of the network. On the left-hand side, you're seeing what our output node or output layer looks like for a simple classical neural network. On the right-hand side, you are seeing the output layer for a quantum neural network, which is sometimes also called the measurement layer. But I think I always feel that naming it as output layer is sort of, better way of, better terminology, I would say. Right. Now let's get into the details of parts of a quantum neural network. Right. So we just, briefly saw each of the component, right? Each of the part of the quantum neural network, and now we will see each of these three different parts in details, right? Okay, let's go to the parts of quantum neural network. Again, let me clarify that, the particular example that we are taking is of classical data and the quantum neural network, right? Things can be different. You can also have other settings here, like having quantum data and quantum neural network. And if you can ask, like, what will be the example of quantum data? So if you are working in a problem like, say, high energy physics, so maybe you say you are working at CERN, right? You are dealing with high energy physics data and stuff that you are getting from Large Hadron Collider, maybe, right? Then that could be an example of, quantum data, right? So I'm just trying to make a point that, you can have different types of settings, but the reason that I have chosen this classical data and quantum neural network is because this is the most popular setting that you will come across, right? So if you're working on a project of your own, or tomorrow you go for internship, or if you're working at a company, this is generally the setting that you will come across, classical data and quantum network, right? And that is the reason I've chosen this. Okay. So what you're seeing in the diagram is the classic simple training loop. That would a typical training loop. What a typical training loop would look like for a quantum neural network, like, with classical data, right? First of all, you have the data input, obvious, right? Here, what exactly you are doing is, converting your classical data into a quantum network, right? That's that, and that's the only role of data input layer, right? Just take the classical data, convert it to quantum state. That's all. Then process data. This is basically the actual learning part, where the actual learning part comes from, right? Where the input data that is being absorbed in the input layer, you process it through your network, and finally, then you extract some output, right? You get some output. What you do is give your output to optimizer. Obviously, you will take that output first, using some loss function, you will get some loss value. And eventually that loss value will be fed to optimizer. And in turn, what that optimizer will do, it will change the values of weights here. So what are the weights here? If you see this layer, right? If you see the values here, phi 1, phi 2, phi 3, they are your weights. And your optimizer will optimize those weights, right? Don't worry about it. We are going to go into the details of each one of these. So, right. But this is just to give you a, broader look, before we get into the details. All right. So the input layer, which is, generally called an embedding layer as well, right? So in the literature, many times you will just come across this as an embedding layer. And as I just told you that, uh, the purpose of embedding layer here is just to take in the classical data that you have and convert it to a quantum state. And again, just to clarify, your classical data could be some tabular data as you're seeing here, or it could be some image that you are seeing, example of of an MNIST image that you're seeing, or as third here, for example, you're seeing, some time series data. Irrespective of what type of data you have, you just push it, through the embedding layer, and you get a quantum state, right? Which is again denoted by cat psi here. Okay. So what would be an example of embedding layer, right? Let's see uh, the most simplest embedding, which is the binary embedding, right? So what you do here is, right, suppose this X is your feature vector, right? So this is an example. So, 0, 0.2, 0.9 is one of the rows in your tabular data that you have. It's one of the rows in your table, and it becomes eventually the feature vector for your model, right? So in binary embedding, what you do is that you decide the threshold, right? And that threshold could be say 0.5, right? Depending on the problem, and just a guess initially, maybe just a threshold. Now, if your feature vector value is greater than or equal to threshold, then what you do is you apply a NOT gate, right? Basically, obviously, when you have a quantum state, right? Initially, the initial state is always state zero, right? So assuming that again, when you will apply a NOT gate, it will be converted to one. What happens if the feature value is less than threshold? You don't do anything, you keep things as it is. Apply identity, basically that means you're not doing anything. Take this example now. So for example, our threshold is zero point 0.5, right? So you took this value zero. Obviously, it's less than threshold. So you don't do anything. Get zero stays as it is. Now you have this second one, zero point 0.2. You don't do anything, obviously, because it's again less than 0.5. The value stays as it is. Now you take the final value, 0.9, and now again you check, obviously it's greater than the threshold of 0.5. So you apply the X gate or the NOT gate. Now it's changed to 1. Now, if you see on the left here, you had a classical feature vector that you have successfully transformed into a quantum state, right? And that was the goal, right? Whatever classical data you have, convert it to a quantum state. Yeah, just a quick note. As I just told you, right? We are just assuming that initial state is always at zero for a qubit, and this is just the matrix form of the NOT gate. I mean, if you would really want to do the matrix multiplication, right? But yeah, a quick note, a more quick note on binary embedding. You generally don't use this in real world. Why? Because if you see there is a lot of loss of information here. Why? Because whether I have values of 0, 0 0.2, 0.3, 0.4, all of that is converted to get zero, right? So there is no difference between 0 or 0.4, right? And the same goes for 0.5, 0.6, 0.7, 0.8, 0.9, or like whatever the values. You know, there's no difference between them, right? It's all being thrown to cat one, right? So that's why there's a huge loss of information in this sort of embedding. So that's why you generally try to avoid it in machine learning, quantum machine learning. So what you use, right? Okay, so I mean, I told you what you should not use, but what you actually use then? What we actually use is angle embedding. Uh, Now again, if you see this angle embedding, this angle embedding is actually a non-linear method, right? And that is the reason this is generally the first choice. So whenever you're working on a problem, a general first choice would be, to use angle embedding, right? And again, it's not like you have a fixed set of options for embedding methods, right? It's not like that. You can create your own embedding methods as well, right? The end goal, always remember, the end goal is to convert your classical data into quantum state, right? It's not like you have a fixed set of options. You can always devise your own methods, but angle embedding is generally the first thing you would try. Again, if you see, we have the same feature vector, 0.2.9. Now, if you remember from that mathematics slide, I had shown you this Rx gate, right? There it was thetas. Here it's x, but it's basically the same matrix. Again, what you do is, you take each value, say first 0 here, substitute it with x, get the value for the matrix, get the state, phi x. Again, substitute the value for zero point 0.2, for x equal to 0.2, calculate the matrix, you will get phi x2. Then repeat the process for 0.9, substitute for x equal to 0.9, calculate the entire matrix, you will get phi x3. which is basically this, right? So again, if you see, you took your classical data from here to a quantum state now that looks something like this. Again, the end goal is just that we're converting your classical data into some quantum state. Angle embedding is generally a first choice. Why? Because it's a non-linear method. It generally works well, but it's obviously not the only choice you have. You can always experiment, create your new methods as well. End goal is just to convert your classical data into a quantum state. Another quick note, angle embedding is a popular first choice, as I told you, and it's non-linear embedding. That's why it generally works out well. Okay, enough time on the embedding part. Let's get to the quantum hidden layers, which is a little more complex. And obviously, what I shown you in that training loop slide, it was a very small example of quantum hidden layer, just one block I had shown, but this is what a general quantum hidden layer could sort of probably look like. In a quantum hidden layer, again, you have two segments, right? The first is what you're seeing in the green blocks, which are called the variational layers, right? And as I told you in the training loop slide, these has all these layers, these variational layers, has these values phi's that from phi 1 to phi 9, for example, here. And what you will be doing is that these values that you have phi 1 to phi 9, you will try to optimize them, right? These are the variational layers. Now, welcome the entanglement blocks, right? So this is the second general component that you would see. So this is a general second component that you would see, you know. And actually, what is a quantum hidden layer? A quantum hidden layer is generally a combination of two. So a variational layer followed by an entanglement block is generally termed as a quantum hidden layer, right? And you apply it in, you sort of stack it on one top of another. So just the way, in classical deep learning, in a classical neural network, you keep stacking, hidden layers, right? It's the same thing you do here, that, you have the first hidden layer here, then you have second hidden layer here, right? And the reason, I mean, as general rule of thumb, you don't end with an entanglement block. You generally end with a variational layer, right? So this is what a quantum hidden layer looks like. And again, we'll go into the details in the hand calculation. I'm just trying to save time for that. But a very quick note that a lot of researchers, sort of like to eliminate this entanglement block in their quantum hidden layer. Why? Because, I mean, as I told you, right, what you're trying to optimize is the weights, right, of the variational layers. So you're optimizing nothing on the entanglement blocks. So, I mean, why to keep them? That's the argument. But a lot of researchers like to keep entanglement blocks. Why? Because entanglement is something that is difficult to simulate classically, especially as the number of qubits goes up, right? It gets more and more difficult to simulate entanglement classically, right? And so when you have this entanglement in your network, you already know that this thing is difficult to simulate classically, right? So that is one of the reasons people like to keep entanglement in their networks, right? But again, what I mean, if you're working on a problem, what I would suggest you is that try both. First keep the entanglement and then remove it. See if there's a performance drop or something, right? But I would always suggest try both of them. All right, let's come to the final part. So if you recall again, we have seen the embedding layer or the quantum input layer. We have already seen quantum hidden layer. Now it's time to see the quantum output layer. And if you observe, quantum output layer is just the exact opposite of the quantum input layer. So as I've tried to say recite this so many times, that a quantum input layer takes some classical values and converts it into a quantum state. Quantum output layer just does the exact opposite, right? It will take some quantum state that it's getting from the hidden layer, right? And it will convert it to some classical values. So what are these classical values? It depends, on the way, on the problem. Like if you are solving a regression problem or classification problem, what exactly are you trying to do, and how what is your loss function, how you are trying to interpret the output. Depends on a lot of factors, but what you would generally see is it could be a probability state vector. So based on the size of the system, based on the number of qubits you are having in the system, you would have 2 to the power n uh, state vector, right? So based on that, you will have a probability vector, right? Probability of the system collapsing in each of the state, right? Probability state vector, or just the state vector, right? The state that you have at the end, maybe. Or you can have a bit string. So if you're say using a real QPU, right? I'm sure in the previous sessions you might have come across this, bit string representation, right? The system just collapses in 0 or 1, and then you get the bit string out of it, or expectation value, right? So any of these depends on how you are trying to use your quantum neural network for what is exactly the problem you are trying to solve. Based on that, it would differ how you are extracting the output. But if you notice, all of these values are some classical values, right? All of them are classical values. So that serves the purpose, right? So your quantum output layer will take some any quantum state that is provided to it, and it will convert it to some classical values. That's the end goal, right? Okay. So again, as a next step, I think it's obvious, but I'll still list it, that once you have these classical values, you will feed it to some loss function, right? Based on the regression or classification problem, whatever you have, it could be mean squared error, cross entropy, depends. And from that, once you have fed the prediction to the loss function, you will have some loss value that you will feed to the optimizer, right? And that optimizer will change the weights of your quantum neural network, right? And the cycle goes on, right? Recap. I hope this picture now looks, much more clearer, that you have some data, right? You convert that classical data into a quantum state by using a embedding layer. Now it's time for the quantum hidden layers and the output layer to chime in. The hidden layer that you're seeing here, it will process the input that it got, provide a quantum state to the output layer. This output layer in turn will give you some classical values, which could be probability state vector, bit string, expectation values. That output that the output layer gives you, it will go to a loss function, right? And that loss function will obviously give you a loss value that will be given to some classical optimizer like Adam, say, for example. And that Adam will then, optimizer will tweak the value of these phi's to optimize them, or for example, to minimize the loss function, it will optimize the weights, and the loop will continue, right? So I hope that was clear. And now it's probably time to go into the depth of this entire thing. So whatever you have seen up until now, graphically, visually, now you are about to see the mathematics of all of it, right? So, if you want, you can get a pen and a paper if you actually want to follow along or so. I'm not really sure you should. I mean, it will go a little faster. But I mean, if you want to, just take notes. Okay, forward propagation. So, I mean, if you know classical deep learning, right, you generally have this forward propagation and back propagation. So forward propagation is obviously, how the model takes the input and eventually, gets an output out of it, right? That's the forward pass. And the back pass is, based on the prediction made by the model, how you change the weights of the model, right? That's the back pass. So it goes from the output through the layers. Forward pass goes from input uh, to the through the layers, right? So forward pass goes from left to right, and the backward pass or the back propagation goes from right to left, right? So now we are about to see the forward propagation inside the quantum neural network. So when you have the classical data, right, mathematically we will see how you reach up to the final output of the quantum neural network, right? Let's do it. Again, I took that favorite feature vector of mine, and what we are again still doing is just keeping angle embedding, right? Again, because it's a popular choice. Uh, so say you are having this feature vector, right? And you want output for that. So in this example, we will use this feature vector and go through until the very end where the quantum neural network actually gives you some output. All right. Again, the same metrics, right, that I already shown you. What you do is take each value and the feature vector 0, 0.2, zero point 0.9, feed them here, right? So theta equal to 0, theta equal to zero point 0.2, and theta equal to zero point 0.9, right? Obviously, the metric stays the same. You just, you know, plug in the value for, each of the values in the feature vector. Okay. If you do so, you get some values for each of the metrics. So, you're getting some values, and notice that some of the values here are complex, right? So when you're working with classical neural networks, you are just dealing with real numbers, right? But when you're dealing with quantum neural network, you will also deal with complex values. That's a very striking feature of quantum deep learning, that things are not real here, things are actually complex. Pun intended. Okay. So file input. What would it be? Now you calculated, right? So what you're doing here is you in the first step you calculated the matrix representation for each one of them, right? But this is the individual matrix, right? You want a final 3-qubit state, right? This is a 3-qubit example. So for that, if you remember from the second slide, you would use tensor product, right? To, you know, for doing this multi qubit operation, right? So you take the first matrix, that you're getting from here. Should I use a different thing just to make sure that things are visible? Okay. So you take the first matrix, plug it here. The second matrix goes here. Third matrix goes here. And please note this state, state zero, right? Of system three, right? Because initially, as I told you, we are assuming that the initial state is state zero, right? So this is the state zero state for a 3-qubit quantum circuit. What you do is just do the tensor product for each of the three matrices. Okay. First, what we'll do is let's just focus on the two, right? So we'll do the tensor product of this, and this will be easier to see. So how it works, right? You take the first element of the first matrix, multiply it with each of the other elements, right? This is this part, right? I mean, it's really easy to follow because you're multiplying with one, right? Okay, let me use another ring for the second one. Now you take the second element here, which is 0, multiply it with each one of them, right? What you get is this one. This is the second one. Okay, third element. Which one should I use? Let's use blue. This is now the third element. Again, the same. Multiply with each of the other elements of the second matrix. What you get is the part here, right? Now, which one should I use? Okay, let's go for orange. Uh, and then you have the final value 1 in the first matrix. Again, multiply with each of the values in the second matrix. You get the second part, right? This is the matrix tensor matrix product for the first two matrices. So up until this step, right, what you have here is a representation of the combined state of the first two qubits, right? This is what you are having right now. You still need to do the tensor product for the third guy, third matrix. Let's do it. Okay, this is what it looks like. Again, if you again just follow along on the same part, right? Take the first value of the first matrix, multiply with all of the others, right? Just keep if you just keep on doing on the same lines, you will get this gigantic matrix of size 8 by 8, which obviously makes sense because you are dealing with a 3-qubit quantum circuit, so it's 2 to the power n, so it's 8 by 8 matrix. Uh, Now what I've cleverly done here is I've written the vector form of that cat00 state. So this is nothing but the vector form of this state, right? That I had shown you that was there in the corner there, right? Now why I've done this? So you have the matrix here, right? That represents the entire state, entire operation that you would do, you know, with those three Rx matrix. This is the entire actual operation. And this was the initial state, right? So when you multiply this matrix with the initial state vector, you actually get this state phi input, right? Which is nothing but this. So this is your quantum state that you get after doing the angle embedding for your classical feature vector that had the value 0, 0.2, and 0.9, right? Again, recall, the only purpose of your embedding layer is to convert your classical values into quantum state. Let me change the ink again, right? So these were your classical values, that have been changed to this quantum state. Again, this is obviously a vector. Again, please don't confuse it, but it's actually a quantum state, right? So again, if I go back in the slide, uh, so that phi input is the state that you get after applying this data input column, right? We are just going through the entire quantum circuit that I just showed you, right? Okay. Okay. Now we are having quantum hidden layers. So you already have that uh, calculated what you get after applying the input layer. Now, again, we will follow the same step. We will calculate the entire matrix, for this, all these variational layers and entanglement block, create a final matrix and multiply it with the phi input state, right? That get vector that we had obtained, right? To get the state at the end here, right? At the end of the quantum hidden layer. Okay. What we do is let's just focus first on the variational layers, right? Let's get the state for them first, and we will focus on the entanglement block later. Okay. So obviously we have three layers here, right? So three variational layers, and we need to calculate the matrix form for each one of them. Okay. So let's start. As I had told you, your phi values here represent the weights, right? So in the training loop, while explaining the training loop, I told you that these phi's are your weights that you will optimize over your training, right? So obviously the first step would be initialize your weights, right? And this initialization step is really, really important. You want to generally initialize your weights with smaller values near zero. Not distribution should not be too small as well, right? That values are completely zero, and it should not be too wide that your values are too spread apart. For example, if you're say you're applying Xavier initialization or something, don't keep the gain values too high. Basically, if you have experience with PyTorch, you understand what I'm saying. Uh, right? So this is a very crucial step that so right now I'm not using any showing any particular type of initialization, right? We are just calling these weights, values from W1 to W9. These are 9 weights that you have, which are basically your files. Okay. So just the way we had, Rx matrix, right, for the angle embedding. Similarly, you have one RY matrix, and the way, for the Rx matrix, you used your elements of the feature vector X, 0, 0.2, 0.9, and substituted the values, right? Similarly, what you will do here, you will calculate RY matrix for each value of the weight vector, So you will first calculate for theta equal to W1, theta equal to W2, theta equal to W3, so on up to W9, right? All right. Now again, we have 3 layers, remember? And as you know by now, that whenever you are doing a multi-qubit operation, you are doing a tensor network, tensor operation, basically, right? So what you will do is tensor multiplication. So in this step two, you have the matrix representation of, each of the 9 quantum gates, right? Each of the 9 RY quantum gates. Now, what you will do is you do a tensor multiplication for the 3 of them for each matrix in each layer for all the gates in each variational layer. You will do this matrix multiplication, tensor multiplication to get the final matrix form, right? Similarly, so what I've shown here in the picture is just the first variational layer, but similarly goes for the second and third. So you will have the second matrix, so matrix representation of the second layer, matrix representation of the third layer. It's very simple, right? Initialize the weights, some random values maybe. Then you have the matrix for the RY, the known matrix for RY gate. Substitute theta, use each value of your weight matrix or weight vector, whatever you want to call. One by one calculate the matrix representation of each of the for each of the gates, by replacing the values W1 through W9. Once you have that representation, matrix representation for each of the RY gate based on the layer, just do the tensor product for each of the matrix, right? And obtain the matrix representation for each of the variational layer. Remember, this is still not the end of the story, right? We got variational layers, but we still have entanglement blocks to take care of, right? So up until the previous steps, up until step 3, using from step 1 to step 3, what you've done is you got rid of the variational layers. You have the representations of the variational layers. Now it's time to calculate the matrix representation for the entanglement block, right? Okay, so again, we have 2 blocks here, entanglement block 1, entanglement block 2. All right. Step 1 will be identifying the control and target qubits, right? So what is a control qubit? I'm sure, all of you here are aware of the C0 gate and its control and target thing that, if the control here is, 1, then, it applies a not here, right? So basically, this is the control qubit, this is the target qubit. So note down that, control and target pairs for each of the C0 gate, and then construct and start with an identity matrix based on the size. So there's whatever number of qubits. So for example, here we are having a quantum circuit of 3 qubits. So we will start with a size of 8 by 8 matrix because to the power 3 is 8. So we'll start with a matrix, identity matrix of size 8 by 8. Now identify the set of all the basis states. So this is nothing but obviously, these are all the possible states, possible basis states from cat 000 to cat 111. All of the combinations, obviously for, uh, each, for whatever the size of the system is, based on that, you will calculate this. So, for example, if you were dealing with a 2-qubit quantum circuit, this would be, 00011011. It will be just 4 if this was a 2-qubit quantum circuit. This is a 3-qubit quantum circuit, so you have, 8 of them, right? Uh, okay, so step one, identify the control and target pairs. It's very easy. You can do it. Second, just create an identity matrix of, based on the size of the quantum circuit. Very easy. Step three, just note down all the possible, the set of the basis state. Again, very easy. Identify the basis state where the control qubit is in one state, right? So wherever your control qubit is in one state, you just create a new set for it. If you check here, that's this, right? Based on the matrix, right? Again, these are the Helmholtz calculations. If you obviously do in the quantum Qiskit or something, you don't have to worry so much about the entanglement part. But we'll do go for it. So if you take the first qubit, right, for this one, you know, the target qubit is in, or the control qubit is in one state. And why one state? Because you know that, a C0 will be activated only when your, uh, you know, the control qubit is in one state. Otherwise, it won't be, right? So if you see for the first C0 matrix, for the first C0 gate, the first qubit, these are all the states where the one when the qubit 0 is in one state, right? If you see all the other ones here, they are all in the 0 state. So for we are doing this for the first entanglement block, right? So for the first C0 matrix, right? So we identified all the basis states where the control qubit, which is the qubit number 0, is in state 1. That is the step 4. Okay. Step 5. Identify the swap state pairs, right? So just this basically, right? So when you apply this, on the second and the third one, say for example, when you are having this, right? When you apply it, the state will change, right? So for example, the 1 2 here will become ones here, right? So whenever you are applying it, 0th qubit, the state will change here, right? So you apply, you get those step state pairs, and then what you do is change the each state's row and column value from 0 to 1 in identity matrix, right? So this. So basically, just notice this part. At 0 1 0 1, you see this one here, and it goes from identity. So if you see, this is first, second, third, fourth, fifth, sixth one. If you see first, second, third, fourth, fifth, sixth one, row to column here, right? Similarly, so your values are getting swapped here, basically, right? And that's how you would do for each C0 gate. And this could be a little confusing at first, I understand. And this is just obtaining the representation of the C0 gate, right? And I mean, if you see a normal C0 gate, it's just the identity matrix, and then it just 101, right? 0 1 0, something of that sort, right? And then you have all the other is just an identity part. It's just this, but it's when you're having 2-qubit system, right? Then it's simpler. But because we are dealing with this 3-qubit system, right? We are dealing with this 3-qubit system. You have to deal with this complicated uh, calculations. Now, entanglement, what is entanglement block 1 and block 2? So, I mean, if you see, these are just 3 pairs of C naught gates. So you repeat step, 1 through 6 for each of the C naught. Each C naught, you are repeating those steps to get the representation of entanglement block 1 and entanglement block 2. And then finally, what you're doing is just matrix multiplication. So the phi input state that you had obtained, after applying the input layer, right? That calculation, remember that vector, that you multiply first it with the matrix representation of layer 1 that you have, then multiply it with the matrix representation on entanglement 1 block, then layer 2, then entanglement layer 2, and then the layer 3. So after all these matrix multiplications, you will have phi hidden, which is the state that you get after applying all the hidden layers, right? And obviously, if you're doing this penny Qiskit, you don't have to worry about all of this. It's sort of running short on time, so let's get to the output layer. Okay. So again, your output layer is just a vector of size 2 to the power n number of qubits. Now, say for example, you are taking the probability state vector, and this would be squared, or a bit string, state with highest probability, depends. But something to note that the state vector, the what you get before, the layer here, the probability state vector will always, will define this. This is Bond's rule, because obviously your probability state vector is, representing the probability to find the state in any of the following basis state, right? So alpha 1 is the probability of getting this state, alpha 2 is probability of getting this state, and so on, right? So these are all the probabilities, and probabilities needs to sum up to 1. So this is Bond's rule that it must adhere to. And amplitude embedding, basically it's another popular embedding, but it's a linear embedding, and for multi-class classification also, you should not use amplitude embedding. Go for instead angle embedding. But if you are in solving a problem like say binary classification, maybe amplitude embedding is something you can use. And in fact, I mean, the reason I put it amplitude embedding is because there in the amplitude embedding, what you do is take your feature vector and and put them inside these amplitudes directly, right? So that's the amplitude embedding, whereas the amplitudes come into the picture. But again, if you're using output expectation values or a bit string, uh, you know, if you're using on a simulator, then it's a different situation. That's where you're seeing the mathematics. But if you are using on a quantum computer, then it will directly come from a computer, and if obviously there will be noise, so you will have a number of shots there, and you will perform it over many times, to get the statistically correct state, right? Okay. Okay, expectation value again. So again, this is where a little quantum part comes in. So observable is a very important part that comes from quantum mechanics, and observable in quantum mechanics represents the physical quantity. Right. So if you those are postulates of quantum mechanics, these things come from there. And again, this is how this is the hidden state, right? Say for example, this is a hidden state vector, the vector you get after applying the hidden state. This is the those values. This is the complex conjugate, right? The dagger of that state, and then this is I guess this is observable, right? Observable matrix. So if you see here, right, this is the actual calculation, right? So phi hidden state is nothing but this vector. This hidden state is nothing but this vector, and the observable here says, for example, the z poly z, right? So what you would do is, do tensor multiplication with identity twice. Why? Because, it's a three-qubit quantum system, right? So when you have that, observable matrix will become size 8 by 8, right? Plug it in here, do the multiplication, you get the expectation value, right? Uh, so each over, let's recap on the output layer, you know, probably state vector, the squaring, the, state vector, right? Then bit string is just the state with the highest probability. And the expectation value is a little more complex than that. But, it's again simple matrix multiplication. The state you have, complex, conjugate of that, complex conjugate transpose of that, lugging things here, and, obviously calculating this observable matrix of appropriate size, and then, finally solving for the expectation value. Okay. And with that, okay, so we are done with the forward propagation, right? So whatever the value you get, as the expectation value or the probably state vector bit string, that is the final value. That would be considered as the output of your quantum neural network. Now you've got the final value, but it's time to back propagate. Change the weights for minimizing the loss function, right? Okay. So, major part of that propagation is just calculating the gradients, right? So, in classical neural networks, you must be aware of, gradient descent algorithms, back propagation, how you use loss function to, you know, so for example, automatic differentiation, right? Those things. Now, in gradient evaluation in quantum neural networks, again, we use this for back propagation part. The first one and the most important one is, parameter shift rule that you're seeing here. Okay, sorry. The parameter shift rule, right? We'll see this in a bit because this is the most prominent one, that you can do on your simulator as well as, on real QPU. And then you have classical backprop, and this is just like how, we store intermediate values and then use chain rule to get the gradients, right? The problem here is that, as you might have guessed, that classical backprop is like, backpropagation, right? This doesn't work on a real QPU, obviously, because, you can't store intermediate values in real hardware, right? And then you have adjoint differentiation, which is, again, variant of the backpropagation, which sort of takes the advantage of the fact that, U and U dagger will be identity, right? So this is a principle basically that it uses, that, if you apply the complex conjugate transpose of a gate, that results in identity. Basically the computation is in quantum computing is reversible, right? So adjoint differentiation takes advantage of that. And it's not like these are the only methods for gradient evaluation. Let me be very clear. There are many more than this. And in fact, Penny Lynn itself offers, I think, 5 to 6 of them. And it's an ongoing area of research that, how you can improve this part, right? If your quantum circuit size is smaller, backpropagation adjoint differentiation should generally work out better. But if your circuit size is really large, say, then the problem is that, simulating things on a simulator gets really difficult, and then you will have to move on to real QPU, real quantum hardware, and then there you will require parameter shift rule, right? Because on real hardware, backprop doesn't work, right? So that's backpropagation, a very bird's eye overview. Quickly going on to the parameter shift rule. This is what it looks like, right? So F is nothing but, your quantum circuit basically. So parameterized quantum circuit, whatever, parameter value is like. So for example, you're doing this with respect to theta 1, then theta 1 plus 5 pi by 2, theta 1 minus pi by 2, evaluate the circuit, get the value, right? And then, evaluate this to get df by dou f by dou theta 1, right? Again, it's just the same that I told you, right? Get wipe rate from the forward propagation, construct a loss function, get a value, right? So, and based on that, then, calculate the gradient. Okay, I have, parameter update is sort of remaining here, but it's just that, W old equal to W old minus alpha into this gradient. It's the same update rule that we have for the classical neural networks, right? And it's just parameter shift rule. And as I told you, there are many more methods of doing things, of calculating gradients and updating your weights. Again, the major part of backpropagation is just based on the loss function and the prediction of the model. You calculate the how would you minimize, how can you minimize the loss function, and based for to minimize the loss function, how would you change your weights, right? This is the end goal of it, and generally use gradient based methods for it. And I showed you that parameter shift rule is one of them, and parameter shift rule agent differentiation, there's SPSA, right? There are many variants of doing this, but again, the end goal is how to tweak your weights to minimize your loss function. That's the end goal. Okay. So the last part for the section, right? Then we'll have the break. Okay. So what will the challenges when you're actually training a quantum neural network, right? I've listed two here, but there could be definitely be more. And I've listed data encoding as second, but actually that should be first, to be honest, because whenever you have some classical data, how do you encode it, right? That's the first question you would be answering. So tomorrow you go out there, in a company, you're working on a quantum machine learning project, and you are given some classical data. You've told that, let's create a quantum algorithm, quantum neural network for this. The first question is, how to encode your classical data into a quantum state, right? As I told you, angle embedding is generally the first choice, but it's never the only way of doing things, right? So many a times, what happens actually is that most of the times it does happen. And I showed you in binary encoding example that there's a lot of loss of information, right? Uh, in angle embedding, it's less, but there's a loss of information, right? So the objective and the step of data encoding is that uh, you know you are minimizing this loss of information as much as possible, and distribution of that quantum states that you are getting after the encoding step, that distribution sort of resembles and is as close as to the distribution of the actual data set, right? So your model is not learning something else, it's actually learning the data. So data encoding is a very crucial, very difficult step. The second, again, that sort of I not listed here, is finding an insights, right? What will be the structure of the quantum neural network? So embedding is just the first part. After that, whether to keep entanglement blocks or not keep it, whether to use RY blocks or RX blocks or RZ blocks. Generally RY blocks work well, but how do you keep RY blocks and then RZ blocks and then follow it with an entanglement? If entanglement, which type of entanglement is linear entanglement, full entanglement, circular entanglement? So which type of entanglement will it follow? And then again, how would you then extract the output? Will you extract it as bit string, or probably state vector, or expectation values? Those things, those are the choices you will make as a quantum machine learning engineer, right? But apart from those simple choice based problems, another is barren plateau, which is sort of the quantum counterpart of vanishing gradients, right? Sort of. So what will happen actually is we'll keep on training, but the model will not learn anything, right? And mathematically, how you define is that the distribution of the variance of the distribution of weights, of the gradients, sorry, almost goes to zero. So basically, there are no gradients coming in, and obviously, if there are no gradients, the weights are not being updated, And if the weights are not being updated, if the weights are the way they are, right, that means there is no training happening, right? So even if you keep training your model for thousands of epochs, you will see that the model is not learning anything at all, right? And that is because there's no gradients coming. Okay, I think it's time for the break. We shall come back to quantum GAN once the break is over, and we'll go for the hands-on session. And we can have the Q&A right now, or uh, maybe after the session.
Well, there are some questions in the chat box. You can see if you can see.
Oh, okay. Mm, kindly explain the negative significance of the negative sign. There's no such. I don't think there's such significance, right? It is just the, so as I told you, it's complex values. So whenever we're dealing with, classical deep learning and all, it's just real values. But here things are complex. That you are having complex values. These are just some values. There's no such, significance, right? Uh, what you can actually do is, uh, apply the explainable AI methods here, to actually see the how things are differing. So for example, I think it's called the neural network playground or something, machine learning playground. I think it's a website developed by TensorFlow. If you see, you can have a classical neural network there, and you can see the feature learned by each node, right? You can sort of create something very similar where you can see what each qubit or a key, each hidden layer, maybe if not the qubit, has learned, and you can see that how the things are varying with the signs of it. But in particular, these are just values, and it really doesn't affect it that way. So each single value will probably not have much of significance. But if a large set of things are becoming negative or complex, then I think you will have something. But it's difficult to just say from the values itself, right? So you will need some explainable AI technique, just the way we have in classical neural networks, right? Because this is black box models, right? So you will sort of need some explainable AI technique to actually understand, based on the problem you are trying to solve, that how those values are actually affecting. According to your experience, what is better for QDRL, Julia or Python libraries? See, Julia, Rust, these things are getting important, definitely. But this depends on what level are you on in your quantum machine learning journey. If you're just getting started, right, Python is your way to go. Python is very simple, and you have, I think, in most of the previous lectures or so, I think people, I mean, the speakers must have used Qiskit. But for quantum machine learning, I would suggest you to go for Penny Lane, right? Because Penny Lane's focus is completely on quantum machine learning and quantum chemistry, but like, we care about the quantum machine learning part. And Penny Lane integrates really well with other deep learning frameworks like PyTorch, right? So I would highly suggest that if you are a beginner, focus on Python and especially Penny Lane. If you want to get into quantum machine learning part, if you're not a beginner, I would say go for Julia. I would say even go for Rust, right? Make things more efficient, right? Maybe create a quantum machine learning library of your own. Why not? But I mean, that depends on where you are in your journey. How much is there a difference in normal DL and quantum DL in terms of quality or speed or any other parameters? Okay, you know what? Let me talk about my research paper on this, right? So, uh, my work, a lot of my work is in physics informed machine learning. Now, this is not a very well known area, right? I mean, if I say computer vision or natural language processing, I'm sure everyone here knows that, understands that. But physics informed machine learning is a less talked aspect, which is say which what is and the most prominent say the basic algorithm there is PIN, which is PIN, which is physics informed neural network. And what is the neural network? Basically, I mean, it's still a normal architecture neural network. So, some input layer, hidden layers, output layer, same thing. But what a pin does is that it solves partial differential equations, right? And so your loss function is not mean squared error or binary cross entropy or something of that sort. Because you're solving a partial differential equation, your loss function is actually a partial differential equation or and the associated boundary conditions and initial conditions. So that becomes your loss function. Whatever PDE you are trying to solve, that becomes your loss function in a pin setting. And if you see, pins generally struggle with generalization. So say you are having a PDE that you solve with a particular value, say there is a particular property constant there, and you solved, based on that. If you change the property constant, you will generally have to retrain the entire model because pins lack generalization. So one of the research papers that I published last year uh, was on QA pin, which is quantum assisted physics informed neural network. And what basically it did was replace the first hidden layer with a quantum variation quantum circuit with a quantum hidden layer, just like the hidden layer I showed you today, a hidden layer of that sort. And I keep the rest of the architecture intact. And what the results were that we solved a viscous Burgers equation there, and the QA pin, gave a reduction of almost 20% with respect to weights, while performing at par with the classical counterpart. So we gave a comparative analysis with respect to, you know, laugh pin, which is sort of state of the art pin, right? Back then at least, and a classical vanilla pin. And what we showed was that the QA pin was performing at par or better than the classical counterparts, right? The reason being that the quantum layer was, giving a compact and better representation because it was, learning with fewer weights, right? So it was getting better representation, and that's why reducing the weights is how actually it helped the model. So the model is not particularly quantum, right? But it's hybrid. But the quantum part, how it helps is, by helping reducing the weights and giving a better representation. So whenever I would say in a quantum DL is I mean every time whenever I go for a session or even if I post anything on LinkedIn, the first thing is always how quantum AI is better than classical AI, prove it. But the framework that I try to follow is you know see where classical AI is struggling and see how quantum can help in there, right? So the way I used, for example, in QAPN, I saw that classical pen is struggling with generalization, right? Basically it's not able to generalize better. And quantum layer, that fundamentally introduces weights in a completely different way as compared to a classical hidden layer. I replaced it, and because of that replacement, it was getting a compact representation and improved the model's accuracy, right? So I would say there's no general rule that how quantum DL is better than classical DL, but whenever you are trying to solve for anything quantum AI, you have to see where classical counterpart is struggling and how the quantum part can chime in and help in any way, right? It could be accuracy, speed, anything, right? I hope that answers the question. Which domains are more suitable for QML and why?
Hey Joy, will you give me a minute just to I need to announce something. So
Sure,
the
sure.
hands-on session will be on the same meeting. So no one need to leave. Okay, so you can just do your things meanwhile. Just, that's all. Okay, thank you.
Okay, great. So which domains are more suitable for QML and why? See, there are many domains. I mean, obviously, I work in physics and for machine learning, so I would recommend that. But besides that, there are many less talked aspects of quantum machine learning. But if you would tell me to pick up one, I would say quantum natural language processing. And I would give you the reason for it because there are many aspects of quantum natural language processing that are just not explored classically. That things, that the text representations, that are inspired from, say, categorical quantum mechanics and stuff, right? So these text representation, cupcake diagrams you may have heard of, right? So these are, completely a novel quantum thing, right? So quantum NLP is a very unique field, and I mean, it's not an easy field. I would just give a heads up. It's not easy, but it's phenomenal. I mean, it's unique, and it's something you can try if you want to. And if you want to, then I would say you can explore Lambeck, which is LAMBEQ. It is a framework by Continuum. It is a framework focused on quantum NLP, and as a researcher, I mean, if you want to follow someone in this domain, I would say Bob Poick. He's the chief scientist at Quantum, and he has done some great contributions on this field, of quantum NLP. And so you should definitely follow his research if you are interested in QNLP, and you can definitely check out Lambeck. Could you suggest any framework for QML? So framework, as in you mean uh, the penny lane or Qiskit, right? The SDK. So I think I already mentioned it that you can have penny lane with PyTorch or TensorFlow. It supports both. But as a researcher, I generally prefer PyTorch because TensorFlow has this habit of giving more abstractions, right? So that's why I sort of reason. Then there's the reason I sort of prefer PyTorch because it gives you finer control, better control, uh, right? So PyTorch with PennyLane is a sort of preferred combination, but you can use whatever you are comfortable with. But I would recommend PennyLane with PyTorch. What are the commercial applications of QML? So one of them I just mentioned, right? The research that I'm doing, right? Physics in machine learning. So the target industries here are aerospace and defense, right? Very, very critical industries, right? Very, very important industries. And besides that, you obviously have quantum natural language processing because, as I mentioned, they're very unique concepts in quantum NLP that are not explored by natural language processing. And obviously, I don't have to tell you where natural language processing is right now, right? It's everywhere in classical AI. So quantum AI, obviously it's quantum NLP is obviously has a lot of commercial applications. Since QML is better in information density, can I reduce bottleneck in content code to improve? Definitely, you should. You can. So I mean, this is one of the things I've been working on. That you can. So you have in the autoencoder you have the encoder and the decoder part. So encoder could be a quantum and your decoder could be just classical. That's one of the things I was working on. So excellent idea, excellent observation. Yeah, I think that's all for the questions, and we can. I think now we can resume again on uh, 15 minutes, 15:30, right?
Yeah, sure, sure. So the rest of you can ask your questions after at the end of the hands-on session. Okay. And thank you very much for the amazing talk.